The Catalytic Reaction Engineering for Sustainable Technologies Group is committed to finding new tangible solutions for a greener future, turning scientific advances into breakthrough technical and industrial progresses. We operate in energy, fuels and additives, and compounds for industry. The CO2 emitted by energy-intensive industries can be converted into methane to provide energy again, closing the carbon cycle to avoid climate change. Crest Group possesses relevant expertise in the design and synthesis of effective catalytic materials. A wide variety of catalysts for CO2 conversion can be prepared, including highly ordered mesoporous materials, well-defined nanostructures, core shell configurations, and multifunctional mixed formulations. The synthesis route is carefully tuned to maximize the catalytic properties of the material and at the same time to abate the environmental impact, minimizing water and energy consumption as well as waste generation. The structural and physico-chemical properties of catalytic materials can be deeply investigated by employing different characterization techniques. From structural properties to surface chemistry, each key aspect of a catalyst is taken into account. Advanced in situ measurements are also carried out to understand how the catalyst interacts with reagents and products under operating conditions. CO2 emissions can be valorized through methanation. The thus produced gas is chemically indistinguishable from fossil methane, but it has no net impact on global warming. Crest Group at DISAT demonstrates that artificial photosynthesis for producing special chemicals from carbon dioxide, water, and solar light is feasible, as new photocatalysts, colloidal nanocrystals, are designed and synthesized to efficiently exploit sunlight. Mimicking nature, in presence of water, CO2 is converted to carbon monoxide at the surface of non-noble metal-based electrodes, while hydrogen and oxygen are produced by the sun-driven water-splitting reaction. Sustainable and alternative liquid fuels are very promising products of the CO2 hydrogenation. Methanol and dimethyl ether could be used as fuel additives of gasoline and diesel, while the products similar to the crude oil could substitute fossil-derived products. The thermochemical conversion of CO2 and H2 at laboratory scale could be performed in a heated fixed-bed reactor up to 500 degrees Celsius and 30 bars. The products of the reaction are condensed at the outlet of the reactor, collected and analyzed with gas chromatography. The large global markets for ethanol and ethylene demonstrate the urgency of replacing conventional processes with more sustainable electrochemical technologies. In this test bench at the Solar Fuels Lab, simulated sunlight can be used as a source of energy for producing chemicals and fuels like ethylene and ethanol from the co-electrolysis of CO2 and H2O at TIL 4/5 by using copper-based electrocatalysts. This technology can be used for storing renewable energy in chemical bonds, reducing the flow of heat trapping greenhouse gases into the atmosphere. The development of chemical processes and products that are sustainable and harmless for the environment is one of the main goals of green chemistry. Diethyl carbonate is a versatile substance that can be used as a lithium battery solvent, a fuel additive, or a reactive intermediate in organic synthesis. We are investigating the direct synthesis from ethanol and carbon dioxide, as it represents a promising path given the low-cost, renewable and non-toxic raw materials. The reaction is carried out in an autoclave reactor by employing a suitable catalyst. Product analysis is then performed by the gas chromatography mass spectroscopy technique, used to identify and quantify unknown substances. CO2 can be fixed in organic compound thanks to metabolic pathways carried out by microorganisms that act as biological catalysts. Algae, thanks to the light, can provide carbohydrates, proteins, fats and pigments. Other microorganisms can fix CO2 thanks to renewable hydrogen, to obtain solvent and build blocks for polymers. Optimization of substrate consumption and product yield is performed in customized bioreactors providing CO2 and H2 at atmospheric and high pressure. Moreover, the fermentative processes involving these different microorganisms are integrated. The byproduct of a process is used as a substrate for a second one.